Hi, my name is Rodrigo Albuquerque. I'm assistant professor at the University of São Paulo in Brazil. This course is offered to master and PhD students from the São Carlos Institute of Chemistry. All this material can be found at this homepage here. I'm going to follow this book, Molecular Modeling Principles and Applications from Andrew R. Leach. And these are the three references. They may be very informative. This course is divided into 5 parts. In 2 of them, I will discuss the terms of molecular mechanics. Part 3, I will discuss geometry optimization. In Part 4, I will talk about molecular dynamics. In Part 5, I will show some special topics and also very briefly discuss Monte Carlo. Let's begin Part 1. Let's begin making some definitions. According to Andrew Leach, theoretical chemistry is a synonym of quantum mechanics, while computational chemistry is synonymous of quantum mechanics plus molecular mechanics plus simulations, understanding and predicting behavior of molecular systems. Well, molecular modelers use all of the above methods. Still, a distinction can be made on these 3 concepts, and the distinction can be made on the emphasis that molecular modeling places on the representation and manipulation of the structures of molecules and the properties that are dependent upon those 3D structures. The most important part is to understand different methods and to apply them correctly. This is really important. So there are many definitions. Sometimes the student is worried about not being able to describe what exactly is molecular modeling. But the important part is to describe different methods and to apply them correctly. How to describe the energy of a molecule? Quantum mechanics describes using the Schrödinger equation, which is based on the wave function, the concept of the wave function, which carries a lot of information about the molecular system or atomic system. And solving the Schrödinger equation, it's possible to find the eigenvalues, the energies of the system, and the wave function, which can be used to predict the probability of finding an electron in a certain region of space, as well as can be used to predict many different properties. Quantum mechanics methods include ab initio, semi-empirical, DFT, and so on. Molecular mechanics methods don't use any wave function and do not consider explicitly electrons. The molecular mechanics calculates the potential energy for the molecule, here is called V steric, as a sum of terms of potential energy. So it's a very simple approach to calculate the energy of a molecular system or atomic system. General ideas behind the molecular mechanics. Atoms are balls. There are no electrons, so the electron is not put explicitly inside this model, and the balls are bonded to each other by strings. Atoms have a mass and are allowed to have a charge. There are no molecular orbitals and no excited states, as we have in quantum mechanics. Molecular mechanics has smaller accuracy than quantum mechanics for many properties, but molecular mechanics is very fast. It's easy to treat, for example, 10 to the power 5 atoms. So very large systems can be treated using molecular mechanics. We can make a comparison between quantum mechanics and molecular mechanics methods. For geometry optimization of a 29 atom molecule in a certain computer, the same computer, it takes 0.3 seconds using molecular mechanics, 80 seconds using semi-empirical method, which already belongs to the quantum mechanics group, and 200,000 seconds using ab initio method. You can see that in the same time you calculate one single molecule using ab initio at this level of theory, you could make a geometry optimization of a giant molecule with hundreds of thousands of atoms. So molecular mechanics is really fast. The concept of a force field. Force field is embedded in the concept of molecular mechanics. Force field is a group of analytical expressions and optimized parameters that describe the energy, this potential energy that I just talked before, of an atomic or molecular system. Examples of force fields include these here, but there are really many force fields. When you calculate the potential energy of the system, the total potential energy, call it V steric, you can make the derivative, and the derivative of this potential energy with respect to the coordinates of the atoms gives the force acting on atoms. And for this reason, this term is used, force field, to describe the equations used inside the molecular mechanics. Let's see how to calculate the interaction energy, the V steric, the potential energy of the system. First, let's recall how to calculate the very precise, the real energy of a system of many particles, of many atoms. If we use the many-body potential, it's possible to calculate the real energy of the system. So this involves a summation over all particles involving two-body interactions, which depends only on the distance between two particles, plus another summation involving all particles and the three-body interaction, which involves three different distances between the three particles, between every three particles from all particles in the system, plus another term, V4 and plus V5 plus V6 and so on. So there are many terms involved if you wish to calculate a very precise potential energy of the system. If you have 1,000 atoms, there are 6 times 10 to the power of 5 pairwise interactions or two-body interactions. So this first summation here would have this many terms, which is a lot. And the second summation here, the second term, would be composed of 1.7 times 10 to the power of 8 three-body interactions. So the second term here would be giant, and V4 would be even larger. So it's very difficult to calculate two-body plus three-body interactions plus four-body interactions, so on. And for this reason, it's possible to truncate here and consider just the two-body interaction. So this can be approximated as a sum over all particles in the system of two-body interactions, but this is an effective pairwise interaction or effective two-body interaction, because inside it there are parameters that tries to take into account the effect of three-body interactions and four-body interactions, so on. So the molecular mechanics is based on these pairwise interactions, effective pairwise interactions. The total energy is then partitioned into independent pairwise potential terms that carry indirectly many body effects. And here is how we can show the V steric, the potential energy for the system, is a sum of terms, and these terms are pairwise terms, effective pairwise terms that describe the two-body interactions between many parts of the system. This involves, for instance, the bond stretching in this first term, the potential energy for bond bending, the potential energy for out-of-plane bending, and so on, torsional interactions and cross terms and van der Waals plus electrostatic interactions. The first term in this summation of potential energy terms is the bond stretching potential. Let's consider two atoms bound to each other through a string. It's shown here. The behavior of the potential energy when you increase or when you change the bond distance between two atoms is shown here by the blue curve, which is a Morse potential, which is a very precise description from what happens in reality. The Morse potential is given by this equation, where you have three parameters. We have the depth of the well, dE, shown here, and the force constant between the two atoms, and the reference bond distance, this L0, which is shown here. So this is very close to the experimental equilibrium bond distance. This formula describes very well the whole range of distance from the left side to the right side of this curve. But it doesn't have an efficient computation, which means if you have hundreds of thousands of atoms, the computer has to calculate this term many times. And for instance, square root is not very fastly calculated. So besides having three parameters, d, e, k, and L0, the computation is not very efficient. So one approximation to solve this a little bit faster is to use the harmonic approximation, which consists in describing the bottom of the well. This green curve is the harmonic approximation, and we describe just the bottom of the well, where the blue and the green curves, they match pretty well. This green curve is a parabola, and this is the equation that's used to describe the potential energy for the stretching, bond stretching between two atoms. So KAB is the force constant of this bond, and L0 is the reference bond distance. The reference value, this L0, is a parameter, is a reference value. It's not necessarily the experimental value, but it's close to it. K is a force constant for this bond, AB. It's also another parameter. Let's see what happens if the variable of this equation, which is only L, so this distance can assume any value, while K and L0, they are constants, they are parameters. And when the bond distance assumes precisely the same value of the reference bond distance, what happens here? The V equals to 0, which means you don't have any energy penalty associated to this conformation. So when the atoms are separated by a distance of L0, the V is 0. As soon as the bond distance changes a bit, can be smaller or larger than L0, this term here exists and is positive. This positive means the energy is higher, the situation is less stable. A highly stable situation would be found when you have the variable, the bond distance, very close to the reference value. Usually one uses K and L0, the two parameters of this stretching potential, associated to atom types. So I and J, actually this should be capitalized, it's capital I and J, they are atom types. And the small ij terms, they are a variable, they symbolize a variable. So there are many different bonds. And for given two atom types, for instance, sp3 carbon or oxygen of a carbonyl group, you may have a different set of parameters, K and L0. The ij, the capital Ij terms are parameters. And an atom type, what is an atom type? So the computer understands much easily if you use numbers instead of words. So instead of saying I have an sp3 carbon, you can just say is a type 1 atom. If instead of saying I have a carbonyl carbon, I would say I have a type 2 atom, and so on. If you have a hydrogen bound to a carbon, sp3 carbon, you would have a type 3 atom. So you may define many kinds of atoms here. And for each two kinds of atoms, for instance, sp3 carbon, you would have a 1-1 stretching, or sp3 carbon and hydrogen, you would have a 1-3 stretching. For instance, if you have the force field mm2, here are some parameters for the stretching, bond stretching of sp3 carbon. The two sp3 carbons, they would have this reference bond distance of 1.52 angstrom and this force constant. So this would be type 1 or a 1-1 kind of interaction. If you have the same atom types, same atoms used here, but you use another force field, you would have slightly different parameters, as you can see here, by the reference bond distance of 1.5 and the force constant is a little bit smaller. So parameters depend on the force field. Don't try to use one parameter of one force field in another force field. Every force field has a set of analytical expressions and of parameters. And if you have multiple bond stretchings in a molecule, as very often is the case, you can make a summation over all bonds. You can calculate this term, the bond stretch potential, bond stretching for all bonds in the molecular system. When you sum all of them, you would have then the term stretching potential, bond stretching potential, which is shown here in blue. I don't need to say the total bond stretching potential. And just when I show V stretching means the total bond stretching potential. One can improve the bond stretching potential by adding enharmonicity. So you can add more terms here. Instead of having a quadratic term, you may have cubic term and a quartic term and so on. In this case, you may also have more parameters. Here you have a force constant. Here you have another force constant, K prime. Here you have a K double prime. And again, you have the same parameters as the reference bond distance here is the same as here and the same as here. And the only variable here is the Lij. So is the bond distance, the real bond distance. That even every moment this bond distance may be different, but the parameters are constant. So here you see that we have many parameters describing the same bond stretching. And this is of course more accurate in regions far from equilibrium, but it's computationally more expensive because the equation is larger, it's a larger equation and more parameters. The computer will take more time to calculate it. Let's see an example here. How many parameters are there in total for this molecule? The molecule shown here, considering the stretching potential, the bond stretching potential only, and the harmonic approximation. Harmonic approximation is only this first part of this equation. Here we have 4 atom types: sp3 carbon, sp2 carbon, oxygen from the carbonyl, and hydrogen bound to carbon. We can give a number atom type for each one of them. We give number 1 for this here, 2, 3, and 4. Now you can see that we have 6 parameters in total to describe the whole bond stretching potential for this molecule. We have stretching involving types 1 and 2. Type 1 is sp3 carbon, type 2 is sp2 carbon. So we have the sp3, sp2 carbon bond stretching here. We have the same bond stretching here. For this bond stretching, the force constant K and the reference bond distance is the same. They are the same. The variables may be different, so this bond distance may be at a certain point of the simulation slightly different than this here. We also have the stretch involving types 2 and 3, which means sp2 carbon and oxygen here. Then there's just one stretching. For this stretching, we have also a force constant K and a reference bond distance L0. And we have also stretch involving types 1 and 4, which are shown here. There are 6 different bonds involving the same 2 parameters, K and L0. So we have in total 6 parameters to describe the whole bond stretching of this molecule. Note that you may have many different Lij, the small ij, which are variables. So this small Lij is the bond distance, the actual bond distance of each bond here in the system. But the parameters, they are fewer. And again, to make the total bond stretching potential energy, to calculate this potential energy, we just have to sum over all these bonds here using the appropriate parameters. Here we see an example of the force field MMFF94. This is the file of where the parameters, this is part of the file where you can find the parameters. This is the attribution of atom types. You see here in this column you have atom types. This column you have atom classes. So for instance, the vinylic carbon sp2 and generic sp2 carbon, they belong to the same class. Or even the carbon double bonded to oxygen and carbon double bonded to nitrogen, they both belong to the class 3. This column shows the atomic number, this column shows the atomic mass, and here the number of chemical bonds formed by these elements. There are many atom types in this force field. And this the bond stretching potential for this force field specifically has this form. So there is a quadratic term. In total, there are 214 atom types or 99 atom classes. For this reason, there are many more atom types than atom classes. Parameters are given for atom classes. In this equation, we have the force constant given in millidynam per angstrom, and the bond length here, the bond distance is in angstrom. Inside the brackets, you don't have a dimension, and this constant 143 just converts this force constant in millidynam per angstrom to kilocal per mole per square angstrom. So in the end, this term, this potential energy for the bond stretching is given kilocal per mole according to this force field. If you are in the same, if you go down in the same file, this is a very big file, there are the attributions of all atom types, and then you can find the parameters. For instance, here in this line you find the atom types, atom classes, sorry. So the parameters are given for classes. So class 1 with class 1. So this is a bond stretching involving class 1, 2 atoms, 2 alkyl carbon sp3 atoms. There's a force constant in this unit, and there's the reference bond distance. If you see a bond between a carbonyl, alkyl carbon sp3, and a hydrogen attached to carbon, this is class 1, this is class 5. So you see here, class 1, class 5, you have force constant of 4.7 and the reference bond distance of 1.093. So these are the parameters used by this force field. And this force field uses this expression. So these parameters are used inside this expression to compute the bond stretching potential for any system. In this case, we have a carbon-carbon bond. We have the class 1 bond stretching you have here. And here you have the class 1, class 5 bond stretching you have here. The bond bending potential is another third term that you can use to calculate the total potential energy of V steric. This movement, we can have here 3 atoms, and theta is the bond angle. This bond angle is just changing, so the molecule is vibrating, is making this bending of this angle. L1 is this bond distance is fixed, constant. L2 is also constant. The only variable here is the theta, which is changing. You can calculate the bond bending potential as an harmonic approximation. We can use harmonic approximation here. So there's a parabole, and the capitalized ijk terms are parameters. Here we have a force constant, which depends on the 3 atom types I, J, and K. And here we have another parameter, which is the reference bond angle, which also depends on atom types I, J, and K. The only variable of this equation is theta, which along a simulation, for instance, or along a geometry optimization can change. So this term you can calculate by this equation, and this reference value is not necessarily the experimental value, but it's close to it. When I will represent the total bond bending potential as just V band. So every time I show you V band, I'm saying that there was a summation over all bond angles of the molecule. We see here an example of parameters for the MM2 force field involving, for instance, bond bending involving 3 sp3 carbons. The reference bond angle is 109.47 degrees, and the force constant for this bond bending is very small, given these units here. And you can consider atom type 1 is sp3 carbon. So you have atom type 1, atom type 1, atom type 1. You have 1, 1, 1 bond bending potential. Here you may have different atoms, of course, and you have sp3 carbon bound to sp2 carbon, bound to oxygen of a carbonyl group. In this case, the reference bond angle is different, of course, and the force constant for this bond bending potential is also different. This is according to MM2. If we would consider another force field, the parameters are different. Let's see this example here. How many parameters are there in total for bond bending potential? Only in harmonic, assuming a harmonic approximation, which means that parabolic equation. We have the same molecule as before. We have 4 atom types already defined as 1, 2, 3, and 4. And in total, to calculate the total bond bending potential for this molecule, we would need 8 parameters, which correspond to bending involving these types here. Type 414 means hydrogen, sp3 carbon, hydrogen. So these interactions are shown here. So these angles can change. We have bond bending on these angles here, and for all these angles, you can use the same 2 parameters, which means the force constant and the reference bond angle. Now you may have also bond bending involving types 4, 1, and 2, which is shown here. Hydrogen, sp3 carbon, sp2 carbon. These angles shown here. All the 4 angles will share the same 2 parameters, same force constant and the same reference bond angle. Then you may have bending involving types 1, 2, 3, which is shown here. And finally, this bend involving types 1, 2, 1, which is sp3 carbon, sp2 carbon, sp3 carbon. See here, for this bending of this angle, you would have 2 parameters too. So in total, you have 8 parameters. You have, of course, many variables here, because every bond angle could be different from each other in a certain point of a simulation. Again, if you have this molecule, you can calculate the total bond bending potential as a sum over all bond angles in this molecule. So you'd have to sum all these bond angles I just showed before to calculate the final bond bending potential given here. The bond bending potential can be also calculated using one larger equation which considers enharmonic terms, which are shown here to improve the model. So this is beyond the harmonic approximation. And the capitalized ijk terms are parameters. Here you have a reference bond angle, which depends on the atom types I, J, and K. Is the same, and here you have a force constant for the bond bending, and depends on the atom types I, J, and K. Here we have another force constant, K prime and K double prime. So we have more parameters. There is only one variable here, which is this bond angle, which changes along the simulation. And this is more accurate, of course. There are more parameters. It describes a little bit better regions far away from equilibrium, but it's computationally more expensive. So it takes more time to calculate this bond bending according to this equation. Here we have again the MMFF904 force field and some parameters for bond bending interactions. And here we have atom classes. So 111 is a bond bending involving 3 sp3 carbons. We have the force constant and the reference bond angle. And in this case, we have sp3 carbon, and hydrogen. And the force constants here and reference bond angle. So this 115 interaction is shown here. The bond angles, the corresponding bond angles are here. So this kind of bending can be calculated using enharmonic terms. And in the case specific of the MMFF force field, this formula is used. There is a cubic term here. This constant converts K to kilocalories per mole per square degrees. The final unit of the bond bending potential for the MMFF is kilocalories per mole. Another term to calculate the potential energy of the system is the bond bending potential for linear or near linear bonds. For instance, bonds involving sp carbon, like these two here. In this case, this bond angle is very close to 180 degrees. And in order to keep this very close to 180 degrees, we use this potential, which is basically an energetic penalty, which forces this angle to be as close as possible to 180 degrees. For instance, when the theta is 180 degrees, cosinus 180 is minus 1. So this term is minus 1 plus 1 is 0, and the whole bond bending potential is 0. As soon as this group makes a movement and this angle is decreased, you may have some energetic penalty coming from this equation. And this term, the bond bending potential for linear bonds, it's used by MMFF, by the universal force field, by the Dryden force field. Here, Ij, capitalized Ijk, are representing the parameter. And the only variable here is this bond angle. This term avoids linear bonds to become angular. So this is, you can consider this as an energetic penalty. When this term is used, this here for linear bonds, the other usual term of bond bending potential from the previous slide cannot be used. So only one of them can be used. Let's see this exercise. We use the MMFF 94 force field to calculate the total potential energy of three conformations of the water molecule, which are shown here. In this case, we only use bond stretching and the bond bending terms, two terms only. The atom types and class are given here. The parameters for the MMFF force field are given here too. And the MMFF use the units of kilocal per mole. And these are the expressions for the bond bending potential and the bond stretching potential. They are given here. So you can just use, the student can use these two expressions to compare the stability of conformation 1, conformation 2, and conformation 3, and also calculate the relative percentile contribution of each interaction to the total potential energy in each case, conformation 1, 2, and 3. After using this expression, the expression given in the previous slide, we come to this result. The stretching potential, which involves in this case two bonds. These two bonds have different variables, have different bond lengths, 0.2 to 0.9. So summing these two potential energy for the stretching, bond stretching, you have this final value of 12.98 kilocal per mole. And the contribution for the bond bending potential is given here, 0.23 kilocal per mole. Summing the two, we have the total V steric, in this case is 13.21. Making the same for conformation 2, we have 11.18 kilocal per mole. And in the last for conformation 3, we have V steric of 1.08. So this situation here has the lowest energy, has the highest stability. Here in red, you see now the contribution of each interaction. We see that in the three cases, the stretching potential carries most part of the energy of the potential energy of the molecule. In all cases, more than 94%. It's 98, 99, 94. And the bond bending potential carries very little energy in all terms. We see the stability order is conformation 1 is least stable, conformation 2, and the conformation 3, which is the most stable. We can compare bending and stretching just to understand better the result shown in the previous slide. In this example, we see the vibrational modes of carbon dioxide. So there are stretching modes and there are bending modes. And these modes, they have different energies. They have different frequencies too. So here we see a vibration spectrum of the CO2, and there is one peak here which relates to the bond stretching. You see that the energy is very high in relation to the bond bending movement, and here we have a 2.4, around 2.4 centimeter minus 1, and here we have around 500 centimeter minus 1. So these two movements, they have different energy. The bond stretching has much higher energy, and that's why it is also associated to a higher force constant, has higher frequency, and that's why it carries most part of the energy in the potential energy from the previous slide. So vibrational modes have different frequencies or forces associated to them or speed. Let's see now another term. It's called the torsional potential. And torsional potential arises when there's some rotation around one central bond here, as shown in this case. And you see that the three gray atoms are in the pink plane, and these three atoms here, they are in the blue plane. The angle between the blue plane and the pink plane is called the torsional angle. In this case, we have the butane molecule, where rotation can occur around this bond here in the middle. In this case, the two carbons which are shown blue here and here, they have an angle, a torsional angle. Now the four atoms, they have a torsional angle of 180 degrees. This atom, this, and this. There's a better way to visualize this torsional angle when you see along this line of this middle bond here. When you see along this line, you would see this here. This is a Newman projection, and you can see that one blue CH3 methyl group is up, the other one is down, and the two carbon atoms from the central bond are here, just on this point. If you now turn around this bond, you may have this conformation here, where the methyl groups, they are facing each other. The torsional angle here, in this case, is 0, and the visualization of the Newman projection would give this here. This, of course, the two carbons will be exactly one over each other, but in this case we just separated a bit to clarify the visualization. If we keep rotating around the central bond, we can have many situations where, for instance, the two methyl groups are facing each other, so we have a 0 torsion angle here, or the two methyl groups, they have 180 degrees. Here's 180 degrees, the situation, and we can have many situations. And usually we can rotate this very slowly using a DFT or ab initio methods to get a very precise profile of this curve here. So this is the potential energy for bond rotation, where the torsion potential, the torsion angle is changed. And you see there are different energies associated to different angles. And if we need to reproduce this curve, we can use the different expressions which can be used to reproduce this curve. One of them is shown here, where the torsion potential is given by this expression where V1, V2, and V3, there are three parameters, and the variable is the torsion angle here, which is repeated here and here. So this angle is a dihedral or a torsional angle, and the V's are the parameters qualitatively related to the barriers. V1, V2, and V3, they may be interpreted according to MM2. V1 is related to the interactions between bond dipoles. Every bond, atoms may have different electronegativities, and therefore you have a bond dipole associated to this chemical bond. In different bonds, they have different dipoles and they can interact with each other. V2 is related to the double bond character. or hyperconjugation in alkanes, or conjugation effects, while V3 is related to steric interactions between atoms number 1 and 4, so 1, 4 atoms. If you want to simulate a double bond, for instance, you need to use a large V2 parameter. So if you use a very large V2 parameter, the rotation cannot occur around this bond. So this mimics the double bond constraint. The next term is the out-of-plane bending. Let's understand this term by visualizing the situation here. We have 4 atoms I, J, K, and L. This is part of a molecule. For instance, this could be a 4-membered ring molecule here. This could be carbon-carbon and double bond to an oxygen. This internal angle here is 90 degrees, and the sum must be 360. Therefore, this angle is 135 and 135 degrees. Well, when we pay attention to these 3 atoms, for instance, they could be carbon, carbon, and oxygen, you would search for the reference bond angle and you would find a value of 120 degrees. So it's not 135 degrees, it's 120, the reference. And the atoms would try to assume this configuration, would try to make an angle between these 2 bonds here of 120. The only way that this is possible is when this atom goes out of the plane. This is the only way that this angle here, which is right now 135, this will decrease to 120. So this oxygen, if we assume this is an oxygen, this oxygen is computationally forced to go out of the plane in order to achieve the 120 degrees, which is very close to the reference bond angle, instead of having the correct experimental value of 135 degrees. So this is the correct configuration. But because of the reference bond angle of 120 degrees for these 3 atoms, this oxygen would go out of the plane. And this is what happens. So when it goes out of the plane, now this angle is 120 between I, J, and L, and between also K, J, and L would be 120. But this configuration here doesn't correspond to the experimental value of 135. So we need to fix this problem. Therefore, we use the out-of-plane bending term. This corrects this problem, and this is the equation used. We have a force constant. The capitalized I, J, K, and L are related to atom types of I, J, K, and L, these 4 atoms here. And we have the angle, the out-of-plane angle, this angle here, which is shown in this picture. So when this angle is 0, if this is 0, the out-of-plane term would be 0. This potential would be 0. But as soon as this atom here, it begins to go out of the plane, therefore going away from the experimental value, the experimental situation, energetic penalty is applied. So as soon as this angle here is larger than 0, energetic penalty comes and it forces the atom to go back to the plane. So this may be seen as a penalty for out-of-plane atoms. So these atoms would try to go back to the plane. You have, of course, another penalty from this term here, but if you use appropriate force constant here, the energetic penalty to go out of plane is much larger than the penalty to not having 120 degrees here. And this is the variable. This angle can assume any value during a simulation, and this force constant is a parameter. This correction keeps the angle, out of plane angle, close to 0. Let's go to the next term. Let's talk about cross terms. A cross term is sometimes used to improve the quality of the properties predicted from molecular mechanics calculations. Let's begin seeing this stretch bend term. Let's imagine 3 atoms here, and they are stretching. There's a bond stretching between atoms I and J, and bond stretching between atoms J and K. When these atoms are stretching and going in the same direction, sometimes they can be very close to atom J, or at least closer than it's shown here. and there will be a repulsion, electron repulsion between the two. And what would happen in a real system is that this angle here would increase in order to minimize this repulsion. And this is what happens. When the bond distance decreases here, this angle is forced to increase in order to minimize the repulsion inside the molecule. So we see that stretching influences bending and vice versa. One uses then, in this case, the stretch bending potential, which is a cross term. This is the first cross term that we see. It's given by this expression here. Inside this expression, we have the bond distance, a reference bond distance, which is a parameter between atom types A and J, a reference bond distance between atom types J and K, and a reference bond angle between atom types I, J, and K. These capitalized letters are parameters, they are reference values. And here we have three variables. We have the bond distance between I and J, bond distance between J and K, and the bond angle between IJ and K. The three of them can change during the simulation. This is the first constant for this coupled stretch bending potential. The next cross term is the stretch. Let's suppose there is a bond stretching here on the side of the molecule. This atom would move towards the central atom, and there will be some repulsion between this atom and this atom here. So in order to minimize this repulsion, this atom would move away. So we see that both movements, they are coupled, as in real systems. There would be also an analytical expression, a potential term to treat precisely this coupling between bond stretching. Another term, cross term, is the stretch torsion. Let's imagine we have four atoms here and we are going to rotate around the central bond. Right now the torsion angle is 180, but let's rotate to decrease the torsion angle to 0 degree. What would happen? This atom and this atom would be closer to each other, and in order to minimize the repulsion, the central bond would be extended as shown here. So this is a way the molecule finds to minimize the repulsion of these two atoms. Now we have 0 degrees of torsion angle. Also, there is an analytical expression for this case that can be summed as an extra term to the total V steric, or the total potential energy of this molecule. Another term is the bend torsion. So here again we rotate around the central bond. The two atoms would be closer to each other, so there will be an extra repulsion here. In order to minimize this repulsion, this angle could increase, as we see here. So both bond angles here increase, and this minimizes repulsion, which means bending and torsion deformations, they are coupled, in fact, in real systems. There is also an analytical expression to treat this case here. We have also bend-bend. This cross term means when you decrease the angle bend, the bond angle here, you increase the repulsion between these two atoms, and this atom would run away, which means this would decrease this angle here, and this would push the other atom away. So we have also this bend-bend interaction. There's also an analytical expression to describe this situation. All cross terms I was just talking about, they can be used to increase the prediction power of the molecular mechanics. So the properties can be better predicted. For instance, vibrational frequencies are better predicted when we consider in the total potential energy of the molecule, of the system, the cross terms. These are the important cross terms, as I showed before. And again, it's good to remember that different force fields, they would have different expressions to treat every interaction, and also they may use different cross terms, or even no cross term. So it's possible every force field is completely different from another one.